And what we're now going to do, we're going to go to another quiet period, and we're going to look at structure formation. And here's the question in structure formation. In the cosmic microwave background, the difference in temperature between the brightest or the hottest and the coldest regions is 1 in 10 to the 5. So to put that in context, if I can go and find a photo of the CMB. I must have got a photo of the CMB from one of our earlier lectures. Apparently I haven't. Well, here's one. Here's a photo of the CMB from our earlier lectures. So in here, this is a high resolution map, you've got these cold areas in here and these hot areas, and the contrast here is greatly enhanced. So this bit is, 1 part in 10 to the 5 hotter than that bit. Tiny variations. On the other hand, if I go and I look at a picture of some galaxies, and so I can just stick this image in, which is we've also already seen from a previous lecture, but this is just local galaxies, right? The difference in density, or temperature if you like, between deep space and the core of the sun is gigantic. So now we have very large differences in density and temperature. And okay, you might say the core of the sun is not a fair example because you've got other things like nuclear fusion going on there, but even, the core of the Earth, for example, is a very different density and temperature from the intergalactic medium or from the critical density. So how do you go about building structures? And the thing to note is that the CMB has structures in it. It has some regions of overdensity and some regions of underdensity. It's just that they're actually very, very minutely over or very, very minutely under dense, or certainly under temperature. And the temperature and the density here, because of the way you observe the CMB, are a slightly more complex thing to infer, which I'm not going to go into. But nonetheless, this is a fair question to ask. And so let's just ask ourselves the following question. If we take the universe now, any overdensity will collapse on a dynamical timescale. And you can write that dynamical timescale as T dynamic, which is equal to 1 over 4 pi g rho to the half, which is equal to c squared over 4 pi g e to the half, if you want that in energy density terms. And that looks a bit complicated, but it's actually essentially a free fall time. Of course, it's not quite as simple as a free fall time because the matter is falling in with you. But if you think about it, if A is equal to gm over r squared, gravitational acceleration, the time to fall a distance r is just equal to a half at squared. So r is roughly gm over r squared t squared. And for a spherical mass, r here, and for a spherical mass, m equals rho r cubed. Or, roughly. So T is therefore just roughly equal, or scales at least with, 1 over the square root of g rho. And so there's some other sort of geometric factors in here to do with spherical collapses and so forth. But to first order, you could think of this just as being a free fall time. The dynamical time is the free fall time. And you might think, well, why then doesn't everything just fall down? So if you work out what's the dynamical time for the Earth's atmosphere, it's a few hours. So why is the atmosphere not just a puddle at our feet? And the answer is something opposes that collapse. So as things try to collapse, something tries to oppose that collapse, and the thing that opposes that collapse is pressure. And so, think about it. You have an equation of state parameter. W equals kT over mu c squared. And you have a sound speed, or you have a pressure time scale. So, let's have a look at the pressure time scale first. That's pretty simple. The pressure time scale is just equal to the size of your region divided by the sound speed, i.e. how long does it take a pressure wave to cross your region and alert you, so you squeeze it on one side, how long does it take for that pressure wave to reach the other side and rebound, how long does it take to react? And here CS is just the sound speed, and CS is just equal to C times dP by dE to the half. And again, this is stuff which you may or may not be familiar with, and if you're not, it doesn't really matter. P, of course, is just WE. And so the sound speed is equal to CS is equal to C times the square root of W. And so to avoid collapse, your perturbation, when your sound speed, must respond more quickly than your dynamical time scale. So, T pressure is less than T dyne. Setting those two to be equal gives you what's called a Jeans length. So, lambda J equals CS times C squared over 4 pi GE to the half. That's actually slightly simplified. You get the idea. With the correct factors in, you actually get the following. Lambda J, I'll just express this over CS, equals pi C squared over GE to the half equals 2 pi CS times the dynamical time. And so structure forms which things which are larger than lambda j, or the corresponding gene's mass. So structure forms for objects larger than lambda j, or the corresponding gene's mass, mj, which is just 4/3 pi rho lambda j cubed. And structure smaller than this are pressure supported.